So, what really keeps our cities alive? I mean, it's not just the power grid or the internet, right? It's this huge, mostly invisible network that delivers the absolute basics for life. And that's the world of environmental engineering. It's basically the life support system that makes our entire modern society even possible.
Just stop and think about that for a second. You've got millions of people, all packed together, all needing clean water to drink, and all producing, well, waste. How does all of that just work? How do we not descend into total chaos and disease? The answer, as you'll see, is some seriously brilliant large-scale engineering.
All right, so here's our game plan. We're going to follow the path of our most essential resources. We'll look at how we get that clean water to our homes. Then we'll see what happens to it after we use it. We'll also dive into how we manage the very air we breathe. And finally, we'll wrap it all up by looking at the incredible impact of the engineers who design these absolutely vital systems.
Okay, let's dive right into our first big challenge: getting safe, reliable drinking water for everyone. It all starts with figuring out the health of our water sources, our rivers and lakes. Before you can treat water, you have to diagnose it. And for that, engineers use this crucial metric called Biochemical Oxygen Demand, or BOD for short. The best way to think of it is like a blood test for a river. It tells us exactly how much organic pollution is in there by measuring the oxygen that microorganisms will need to break it all down. So if you get a high BOD result, that's a huge red flag. It means the water is sick and it's going to need some serious treatment. So how do we actually get from a murky river to a clean glass of water? Well, it's a whole journey with a few key steps. First up, screening, which is pretty straightforward. It just gets rid of the big stuff, like leaves and twigs. Then things get a little more clever with coagulation and flocculation. Here we add chemicals that act like little magnets, causing all the tiny dirt particles to clump together into bigger, heavier bits. Next, in sedimentation, we just let gravity do its thing, as all those clumps settle to the bottom. After that, filtration takes care of the even finer particles. And the final, absolutely critical step, disinfection. This is where we kill any lingering nasty bacteria and viruses, making that water completely safe to drink. Okay, so once we've used all that nice clean water, we kind of create a brand new problem: wastewater. Every single toilet flush, every shower, every load of laundry contributes to this massive stream of contaminated water. And it all has to be managed before we can safely return it to the environment. Now, cleaning wastewater isn't just a one-and-done kind of thing. First, you have primary treatment. This is mostly physical, using screens and tanks to get the solid stuff out. But honestly, the real magic happens in secondary treatment. This is where we get rid of all the dissolved pollutants, the stuff you can't even see. And then finally, there's tertiary treatment. Think of this like a specialty tool, something you use when you need to remove really specific contaminants, like extra nutrients, before that water goes back into a river or lake. And this is where it gets really, really cool. The heart of that secondary treatment we just mentioned is something called the activated sludge process. This isn't about harsh chemicals, it's all biological. Engineers have basically harnessed nature by creating the perfect environment for a massive population of beneficial microorganisms. We're talking about a cultivated army that literally eats the dissolved waste in the sewage, cleaning the water for us. It's an absolutely brilliant example of bioengineering on a huge scale. So what happens when all that treated wastewater finally gets released back into a river? Well, the river actually has this amazing natural ability to purify itself even more. Engineers model this process with something they call the dissolved oxygen sag curve. See, when waste enters the river, it uses up some of the oxygen. But as the river flows and tumbles, it naturally mixes with the air and slowly brings those oxygen levels back up. And this is how engineers can actually predict what nature is going to do. They use a mathematical model that's basically a balancing act. It weighs the rate that oxygen is being used up by any leftover pollution against the rate that oxygen is being put back in from the atmosphere. This lets them make sure that the treated water we release doesn't overwhelm a river's natural ability to heal itself. It's all about protecting the life within it. All right, let's shift gears. We're moving from the water beneath our feet to the air all around us. The basic challenge is actually the same. How do we safely manage the waste we release? But, managing air quality is a whole different ballgame. Because unlike water in a pipe, air is absolutely everywhere, and it's always moving. To get a handle on air pollution, engineers first have to classify it. You have primary pollutants, which are the ones shot directly into the air. Think of soot coming out of an exhaust pipe. But then you have secondary pollutants, and these guys are a bit sneakier. They aren't emitted directly. Instead, they form up in the atmosphere when those primary pollutants react with each other and with sunlight. And the most famous example of this? Smog. So under normal conditions, the atmosphere is actually our friend. As you go higher up, the air gets cooler. This is called the lapse rate. So warm air near the ground is lighter and it naturally rises, carrying pollutants up and away where they can spread out harmlessly. It's like the atmosphere has its own built-in ventilation system. And engineers actually use this, right? That's why they designed smokestacks to be so tall to release emissions high up into this dispersing layer. But sometimes that whole system just breaks down. A temperature inversion is what happens when a layer of warm air parks itself on top of cooler air near the ground. This warm air acts like a giant lid on a pot, and it traps the cooler, denser air and all the pollution in it right down here where we live and breathe. Understanding this is absolutely critical for forecasting those bad air quality days and figuring out how to protect public health when a city is blanketed in smog. And here's the most important point. All of these solutions for our water, our waste, our air, they aren't isolated things. They are all part of a single, massive, interconnected system designed by environmental engineers to protect our health and, really, to sustain our entire way of life. When you just step back for a second, you can really see how incredibly broad this field is. It's pulling from complex chemistry for water purification, from microbiology for wastewater treatment, and from physics to model our atmosphere. Every single part is a critical piece of the puzzle that ensures our environment can actually support our huge, dense populations. And it's a system that's always evolving, always having to meet new challenges. Which kind of leads to a final thought. We've engineered incredible solutions for sanitation and basic pollution. But now, as we're facing down issues like microplastics, climate change, and resource scarcity, what's the next monumental engineering feat that we're going to need to safeguard our planet's life support systems?